So now I want to talk about what, let's say, based on the Haladan model, tells us when we can get shallower in diving in the stop, the compression stops, and when we know that we are safe enough such that we can get out of water without the risk of decompression sickness. You know, if we are talking a little bit more basically, it's about how much inert gas, what is the pressure of the inert gas in the tissue. If that pressure is high enough, but we get atmospheric pressure that is low enough, this gradient pressure causes the inert gas to form in the tissues to form bubbles. So as we are doing the compression stops after diving or after hyperbaric oxygen therapy, we need to note that we need to reduce the partial pressure of the inert gas enough before we are going low in before we reduce the ambient pressure to lower threshold. Now, how can we know to how much we need to reduce the partial pressure of the tissue, of the inert gas in the tissue, using the decompression stop, so that we can get ahead with getting out of water, ascending in diving or reducing the pressure? For this, we have the what is called in Haladan model the M value. It's more than Haladan model because Haladan model was based on supersaturation, and Haladan wanted that the ratio between the, let's say, the partial pressure of the inert gas in the tissue divided by the partial pressure of the atmospheric that you are in depth now won't be higher than 2, namely P of the tissue divided by P of the atmospheric pressure won't be more than 2, because if it's more, there is a risk for gas development to bubbles. This is the idea of supersaturation. This is the ratio of 2 that was updated to become what is called the M value. Now, M value, as you can see right over here, is again tells you what, based on the depth you are at, based on the atmospheric pressure, ambient pressure that around you, what is the threshold for the partial pressure of the inner gas in the tissue that you need to not get over. I mean, this is the maximum allowable inert gas partial pressure in that tissue, and this is ambient pressure. Now, you see that it means in that tissue because there are different compartments, and for each compartment there are different A and B values for the M value formula. So if, for example, the M value, you can see for different compartments in the body, you remember that there are fast, medium, slow compartments. The model divide our body to 16 compartments. For each compartment, there is a half-life for the inert gas. Of course, as the compartment is slower, the half-life is longer. And for each compartment, there are the A and B used in the M value formula. You can see that how they change. A is decreasing as the compartment becomes slower, and B is increasing as the compartment becomes slower. Now, so based on the compartment, we can get A and B, and based on the depth we are at in diving, we can get the ambient pressure. Now, this tells me for this compartment, in this depth, in this ambient pressure, what is the maximum pressure I can be with the inert gas in that compartment. If I get more pressure in that tissue, the gradient will be high enough such that bubbles will occur and decompression sick, and there is a risk for decompression sickness. Now, of course, in the descending in the diving, I mean, in the start of the diving, the ratio or the pressure in the tissue is always lower than the M value. Because you just start to dive, the tissue just start to accumulate the inert gas. It's relevant when you start to ascend. This is when you can get the compression sickness. Because when you're ascending, you reduce the ambient pressure. But if you ascend too fast, the partial pressure in the tissue of the inert gas still stays too high, like it was in when you was deeper. But when you decrease the ambient pressure, the M value decrease. But if the partial pressure of the tissue is still quite the same, like it was in the more higher depth, so the partial pressure in the tissue of the inner gas might be higher than the M value in this now ambient pressure after you ascend. And this what causes the gradient and the bubbles to appear. So of course you can calculate the ambient pressure based on the formula that 1 for atmospheric pressure at the surface plus how deep you dive in meters divided by 10. For example, for 20 meters dive, it's 1 plus 2, so it's 3 atmospheres in 20 meters of dive. So let's maybe do an example. So if I'm diving to 20 meters, the compartment, let's take compartment 5, so I have A and B values. I can calculate the M value. This is 3.1 bar. So in this depth, the tissue, the partial pressure of the inner gas in the tissue can be up to 3.1 bar. And if you cross it, there is a risk for decompression sickness. So when we are ascending after the dive, we need to ascend slow enough to let the inert gas get out of the tissues such that the partial pressure in all of the tissues, and we need to check for each compartment. I need to let the partial pressure reduce enough such that the next target depth, the more ascent depth, will be with the M value that is high enough such that the partial pressure won't exceed it. This is the idea of M value. It tells us in each depth what is the maximum partial pressure we can have in each compartment. So therefore, this is the reason why in decompression stops, we need to wait until the partial pressure in all the compartments reduce enough until before we get to the next stop, there is a M value for each compartment. We need firstly in the stop to get low enough for each compartment and just then to go to the next stop. But by the time we start to ascend to the next stop, we need to make sure that all the partial pressures are low enough compared to the next stop, compared to their M values. This is the idea of M values. It's the limit that we don't want to cross with each compartment, with each partial inert gas partial pressure. Okay, so this is the M value in Haladan model for the maximum allowable inert gas partial pressure in the tissue at the ambient pressure, depending on the ambient pressure. And for each compartment, we have an A and B. And that's it. And we always need to make sure that the partial pressure of the tissue is lower than the M value in this ambient pressure target before we get to this target. Because otherwise, if it's bigger, the partial pressure in the tissue is bigger than M value, there is a risk for bubble creation and decompression sickness. So we need to reduce the partial pressure tissue before we get to this M or this next stop or next target depth that is shallower, that has lower M value. Okay, so this is the idea of decompression stops, to reduce the partial pressure of the tissue before getting ahead in the ascending, in the dive. Thank you very much. This was about the M value in the Haladan model for diving. This is the limit, let's call it. Thank you very much, and that's it.